So today we have the honor to have as an invited speaker, Barbora Tumpach from the Wolfgang Pauli Institute, Vienna. And she's going to talk about the restricted Grassmannian and its cotangent space from various points of view.
Thank you very much for this invitation. I'm very glad to see you from Vienna. So I will give a talk about the restricted Grassmannian and its cotangent space with different point of view. My point of view originally is symplectic geometry. I will try to make the link with frame theory as far as I can. If something is unclear, please stop me. I have a lot of slides, but I don't need to explain everything. I just prefer that you understand what I'm saying. So please don't hesitate to stop me in some way, either by raising a hand online or just by raising your voice. So this is a joint work. I mean, it's based on a work in progress with Thomas Golinski, Tom Needham, and Clayton Shonkwiler. And the plan is the following. I will mainly speak about the restricted Grassmannian as a symplectic and Kähler quotient. And I will start by defining or recalling what the canonical basis of an element of the restricted Grassmannian is. So this goes back from to the work of Presley-Segal in the book Loop Groups, for instance. And then I will make the link with frame theory. So I will give a frame theoretical point of view and then a symplectic point of view. Then I will go to the cotangent space of the restricted Grassmannian, and we will see that it will be diffeomorphic to a complexification of the Grassmannian. So I will explain this, and if time permits, I will speak about Kähler potentials, but probably I will just show you the formulas and explain, and this will explain what I did before. So let me introduce some notations. So for two Hilbert spaces E and F, F of EF will be the set of finite rank operators from E to F, L1 the set of trace class, L2 the set of Hilbert-Schmidt operators, and B will denote the Banach algebra of bounded linear operators from E to F. And the Fred will be the Fredholm operators. We will use also Banach Lie groups of bounded linear operators. GLH will be the notation, UH for the unitary group. And we will be also interested in a smaller group, GL2, of invertible bounded operators, which differ from the identity by Hilbert-Schmidt operator. And similarly, U2, which differs, so unitary operators, which differs from the identity by Hilbert-Schmidt. So these are the notations through the talk. And the restricted Grassmannian is defined as the following. We start with the decomposition of a separable complex Hilbert space H into two blocks, H plus plus H minus. Both here are supposed to be infinite dimensional and closed. And so the Grassmannian, the restricted Grassmannian is the space of closed subspaces of H, which differ from H plus, which are close to H plus in some sense. So the projection from this closed subspace P, the orthogonal projection P plus onto H plus, is supposed to be Fredholm. And the projection P minus from this closed subspace P onto H minus is supposed to be Hilbert-Schmidt. And we will denote by GRS 0 the connected component of the restricted Grassmannian GRS containing H plus. In all the talk, I will just speak about this connected component. I will avoid saying this is a connected component of H+. I will just call it the restricted Grassmannian, but keep in mind that we are just dealing with this connected component. There are infinitely many which are indexed, or the connected component of the restricted Grassmannian are indexed by the index of the Fredholm operator P plus from a given space to H plus. So to know if P is in the same connected component of H plus, we have to look at the index of this orthogonal projection P plus restricted to P. So we will specify a basis, Hilbert basis from the separable complex Hilbert space H, and we will denote it by En, with indexes in Z, and the indexes from 0, 1, 2, 3, and so on will be the basis of H plus, and the negative indexes will correspond to the basis of H minus. So now I'll go to slowly to the definition of a canonical basis of an element P in the restricted Grassmannian. And first of all, I need to associate it to an element P in the restricted Grassmannian, a subset, S index P of Z, of the integer. And SP is defined as follows. So this is the set of integer S such that there exists an element F of the space P, the closed subspace P, of the following form. F is infinite sum, but only with the finite numbers of positive indexes. So it's a sum from k going to minus infinity to a given S, finite one, of combinations of the element of the basis. And the coefficient F sub S is non-zero. So this subset SP allows to define a subspace, a closed subspace H index SP of the Hilbert space H, simply by taking only the element of the basis which belongs to this subset SP. So the proposition by Priestley-Segal is the following. This set SP differs from the natural numbers simply by a finite set. So if you look at those SP with with positive indexes, you get a finite set, and you have also that n. If you subtract SP for n, you have also a finite set. This comes actually from the Fredholm condition, so you can also understand it by the Fredholm condition. So for every P in the restricted Grassmannian, the orthogonal projection PSP from H onto this particular space H sub SP restrict to an isomorphism from the closed subspace P onto HSP. These subspaces HSP usually are used to define charts on the restricted Grassmannian, so you can also understand it like this. And for any element of the canonical basis indexed by an S which belongs to SP, we can define this element YS from the space P as the inverse image of the element of the canonical basis indexed by S by the inverse of this orthogonal projection. So the proposition before said that this orthogonal projection, when restricted to P, is an isomorphism, so we can invert it, and the preimages of the element of the bases, which are indexed by S, will form the canonical basis of P. This canonical basis is not orthonormal, it's just a Schauder basis. So any element of the space P can be written as a combination of this element of the canonical basis with coefficient a priori only within C. So the proposition that follows is that any element, now we are looking at the connected component of H plus in the restricted Grassmannian. Any element P in this connected component is a range of an application, I denote it YP, from H plus into H, such that the projection, the composition of this application YP with a orthogonal projection on H plus is of the form identity plus a finite rank operator, and the projection P minus applied to this application YP is Hilbert-Schmidt. So here the idea is that to an element P in the restricted Grassmannian, we can associate it this subset SP, and we can order the subspace in increasing fashion, S0 smaller than S1, and so on. And so the linear operator, the linear application operator YP from H plus to H will take an element of the basis En to the nth element of the canonical basis of P. So En will go to Y sub Sn. So this means, in particular, if you write this operator YP in the basis that I have written here, so H plus is a starting space, and then we can decompose the Hilbert space H into two subspaces, HSP and its orthogonal. And this YP is exactly of the form identity in the first block and bounded operator B, which is actually Hilbert-Schmidt for the second block. So this is exactly, if I go back, this comes exactly from the definition of the element YSN as the inverse image of an element of the basis by the inverse of the projection. So we have this decomposition. Now, in the case where the HSP belongs to the connected component of the restricted Grassmannian containing H plus, we have that the index of the orthogonal projection onto H plus is 0. And so for n large enough, S sub n will be equal to n. So there is the same number of integers that we have forgotten and added to n to get SP. And so if you write the identity operator in block form with two different, with respect to two different decomposition, from first we decompose H into the direct sum of HS sub SP and its orthogonal. And for the range, we just use the decomposition H plus plus H minus. Then the identity has the following form where R1, R2, R3, R4 are just finite rank operators, which correspond to a permutation, finite dimensional permutations of the basis elements. So in particular, finite rank. So then if we want to write the operator YP with respect to the decomposition H plus and H minus, so we have to change the basis, and this will give this following expression here. And you see that what we get is identity plus a finite rank operator for the upper part, and bounded, actually a Hilbert-Schmidt operator for the lower part. Yes, so this is a particular operator that give us as image the element P of the Grassmannian we started with. So in other words, we can say that an element P in the restricted Grassmannian is the image of H plus. So here, restricted Grassmannian is a connected component of H plus. An element of this connected component of H plus in the restricted Grassmannian is the image of H plus by an element of GL2 of H, so bounded linear invertible operator, which differ from the identity by Hilbert-Schmidt. And actually the blocks, the diagonal blocks, are in identity plus F. So we have here, just before, an element YP of the with just one column, so H plus is mapped to this operator. And what we do to extend this one column to an operator in GL2, we do the same with respect to the orthogonal of P. The only things that we have to check is that when P belongs to the connected component of H plus in the restricted Grassmannian, then its orthogonal, P perp, is belonging to the connected component of H minus in the dual Grassmannian, which is obtained simply by exchanging the role of H plus and H minus. So we can also get a canonical basis for this element, and this is how we built an element of GL2, which the required property. So identity plus finite rank on the diagonal. Sorry, I moved too fast. These elements of the GL2 is constructed using the canonical basis, which is not orthonormal. So the operator AP is not in U2. If we want to get an operator in U2, we can use polar decomposition and multiply from the right by the inverse of the absolute value of the operator. But we will not keep the property that on the diagonal we'll get identity plus finite rank, but we will get on the diagonal identity plus trace class. So simply when we use the polar decomposition and we kill the non-unitary part, we end up with an element in U2 with block diagonal in identity plus L1, which maps H plus to the element P we started with. So any element P in the restricted Grassmannian is also obtained by the action of U2, and more precisely of a smaller group of U2, which I will denote by U1, 2. So these are Hilbert-Schmidt operators, but with respect to the decomposition H plus and H minus, we have identity plus L1 on the diagonal. Here is a definition. So this group U12, if we decompose operators with respect to H plus and H minus, these are operators that differs from the identity by a trace class on the diagonal, and the off-diagonal blocks are just Hilbert-Schmidt. The corresponding group GL12 is the same, with the same condition. So identity plus trace class on the diagonals and on the diagonal blocks, and the upper blocks are just Hilbert-Schmidt. So what we have seen before is that U12 acts transitively on the restricted Grassmannian, and we used the canonical basis to show this and the polar decomposition, but there are also different proof of this fact in the literature. I refer here to one proposition in a paper that I have with Daniel Beltitza, Teodor Hatziu, and there is another proof by Esteban Ondrushov and Gabriel Larontonda. Actually, the first proof that the first reference uses Hopf-Renaud theorem, and I refer also to the paper of Esteban and Gabriel for this theorem in this context. Now I'll go to an affine space. You can think of this as, it will be used then for defining basis of element of Grassmannian. So here we take all the bounded operators from H plus into H with a similar condition as before. So the upper block is of the form K times the identity plus trace class. K is a non-zero element, non-zero number. You can take K equal to 1 if you want. It doesn't really matter for the rest of the talk. And the lower block is Hilbert-Schmidt. So this space is an affine space modeled on a Banach space L1 for the first block, upper block, and L2 Hilbert-Schmidt operators from H plus to H minus for the lower block. So what we have proved before is, because the canonical basis is of this form, we have proved that any element P in the connected component of the restricted Grassmannian containing H plus is the range of an element in MK. So now I will go to frame theory, and I will give you some definition. I'm sure most of you know these definitions, but let me recall what a frame is for a Klopf subspace P of a Hilbert space H. So a frame is a sequence of vectors in P with the following bound. So there is a number A times the norm of F squared as a lower bound, and a similar upper bound with another coefficient B. And in between, there is the sum of the squares of the projection of the scalar product from F with any element of this sequence. So if A and B are A and B are called the frame bounds, and if they are equal, we say that the sequence is a tight frame. And if they are equal to 1, we say that this sequence is a Parseval frame. I give here two references of Eduardo and Pedro Macei about this theory of frames for subspaces in a Hilbert space. And so the difference I took from this paper, the first paper, and also similar definition also in the second reference that I used. So there are 3 operators related to a frame. The synthesis operator, which so here I will take like H plus instead of L2 of n, I will take H plus as a starting space. The synthesis operator will map any element of the basis En of the initial space H plus to the corresponding Fn of the sequence. So this is the synthesis operator, and the analysis operator is adjoint, which is a bounded operator from H, the ambient Hilbert space, to here H plus. And the frame operator will go from H to H and will be defined by S adjoint or A adjoint A. Let me give another definition, which is the definition of constant norm Parseval frame for a closed subspace P. This is a sequence of vectors in P with constant norm. So each element of the sequence has the same norm. And such that this sequence form a Parseval frame. So another way to define Parseval frame is that the frame operator is actually the identity. And the theorem that we wanted to address in the infinite dimensional setting with my collaborators, Thomas and Clayton, is a theorem by Cahill, Nixon, and Stroh, which says that the space of constant norm Parseval frame of n vectors in CD is path connected. So this is a finite dimensional theorem. I give the reference below. So my collaborator, Tom and Clayton, gave a symplectic formulation of this theorem in this finite dimensional setting. Using symplectic reduction, which we wanted to generalize in the infinite dimensional setting. So let me explain a kind of dictionary between, so the space MK I defined before, it's here a schematic way to express what MK is. These are operators with two blocks. The upper block from H plus to H plus is K times the identity plus a trace class, and the lower block is Hilbert-Schmidt. And this space is isomorphic to the dual space where we just take the adjoint of any operator in MK. So A in MK is mapped to A star or A adjoint. And if A is injective, so the corresponding S is surjective, A star A corresponds to SS star, and A star A equal to identity means that A is in the Stiefel manifold, and this corresponds to SS star equal to identity of H plus, which means that the corresponding sequence is a Parseval frame. So here I give the reference to a paper by Gustavo Corrach, Pacheco, and Stoyanov, which studied the epimorphisms of frames. So when the map S is surjective, and in my case, I will have injective maps. So you can use this dictionary. Now I go to the symplectic point of view. And I need to define what a symplectic form is. Usually this symplectic form are weak. So a weak symplectic form on a Banach manifold is a closed non-degenerate 2 form on this manifold. So closed as a 2 form and non-degenerate in the sense that the map that takes an element X to the inner product of the symplectic form by X is an injection. Usually it's not a bijection, as it is the case in the finite dimensional settings. It is just an injection, but this tells us that the kernel of this symplectic 2 form is 0. I'll give a simple example. The affine space MK I just defined before. So it is a symplectic flat space. It is modeled on L1 times L2. And symplectic form is simply the imaginary part of the trace of x star x if x and y, x star y, when x and y are 2 elements of the tangent space of MK. So this is a simple flat space, symplectic space. What I will need is actually the definition of a Kähler manifold. So a weak Kähler manifold is a Banach manifold endowed with a weak symplectic form, and also a Riemannian metric, G. So a Riemannian metric is symmetric form at each tangent space, which vary smoothly when we change the foot point. And this symplectic form and the Riemannian metric are supposed to satisfy a compatibility condition, which is the following. We can define an operator I because the symplectic form is non-degenerate. The symplectic form can be written like Gixy. The symplectic form applied to x and y is of this form, with an operator A, which squares to -1. So it's an almost complex structure in this sense, and it's such that the Nijenau tensor of this almost complex structure vanishes. So this means that it's a formally integrable complex structure. I recall what the Nijenau tensor is. This is here the definition. X and Y are 2 elements of the tangent space at X to the manifold. We extend them into smooth vector fields around the point X. And the bracket here means the bracket of vector fields that we then evaluate at the point X. So we bracket the extension and we bracket different expression where the almost complex structure enter. And if this Nijenau tensor is 0, we say that the almost complex structure is formally integrable. In the finite dimensional case, and also in the analytic case, real analytic case in infinite dimension, this then implies that there are holomorphic charts for the manifold M. But there are also in the infinite dimension contour example where the complex structure is formally integrable, but there's no holomorphic charts. With Thomas and Gabriel, we were interested in more general Nijenau operator than complex structures, and here are 2 references for this. In the case where the Banach manifold is an homogeneous space. And also Daniel Beltitsa has a lot of work on this, but you can find a reference in our paper. So let me go back to my example. MK is a weak Kähler flat space. As I said, it is modeled on L1 times L2. And I already gave you the symplectic form, which is the imaginary part of the trace. The Riemannian structure is the real part of the trace. And the complex structure is simply multiplication by I. So this comes simply from the fact that MK is actually endowed with a complex scalar product. We take the imaginary part for the symplectic form, the real part for the metric, and the multiplication by I is the complex structure. Now I need to introduce what a moment map is for an action that preserves a symplectic form. So the context is the following. We have a smooth Banach manifold, M, and a group G, a Banach Lie group acting smoothly on M with Lie algebra G. And we suppose that the action preserves the symplectic form of the Banach manifold M. The Banach manifold is endowed with a weakly symplectic form, and the G action preserves it. Then we say that the moment map for this action is a map mu from N to the dual space of the Lie algebra of G, which satisfies the following. The differential of the moment map at a given point X is connected to the symplectic form in the following sense. When we pair this differential with an element A from the Lie algebra, then what we get is the inner product of the symplectic form with infinitesimal generator generated by this element A of the Lie algebra. So let me recall that when a Banach Lie group G acts smoothly on a manifold M, its Lie algebra also acts on M, and its action gives vector fields, which are called infinitesimal vector fields associated to the action. So simply, this vector field XA is what we get when we differentiate one parameter subgroup, the action of a one parameter subgroup of TA acting on the manifold. In particular, it gives a vector at X, at the point X, which we can put inside the symplectic form to get one form which eats some other vector. So this moment map mu from M to the dual space of the Lie algebra of G is can be endowed by can be related to an action of G. So G acts on M on one hand, and G acts also on the dual space of its Lie algebra by coadjoint action. And we say that the moment map mu is equivariant if it's equivariant with respect to these two actions, so the ordinal action of G on M and the coadjoint action of G on its the dual of its Lie algebra. If this is the case, then we say that the action is Hamiltonian, and mu is a corresponding moment map. So here is again the equivariance with respect to the action by G on M and the coadjoint action on the dual space of the Lie algebra of G. Let me give an example first in finite dimension. I'll take the space of matrices, of complex matrices with n row and m columns, which is endowed with a symplectic form, which reminds you to the one that we used before, imaginary part of the trace. There are two actions, actually. There is a left action by UN on the left, which is Hamiltonian, and here you see the moment map. So the moment map evaluated at some point X of the manifold of matrices, when paired with an element A of the Lie algebra of the group, gives this number. So trace of X star multiplied with A, and there is a coefficient in front of it. Don't trust me with the sign, it's probably a plus here, depending on the conventions. There is another action of this time the group UM on the right, which is also Hamiltonian, and you see the moment map is very similar. So here we are in the setting where we have a symplectic space with two actions, one from the left and the other from the right. In particular, the two action commutes, and with two moment maps, which actually have compatibility properties, which is actually encoded by the definition of dual pairs. And here I give you a reference about dual pairs, where this example is treated in details. And also the second reference, so the first reference is by Skerrit and Wiesmann, so dual pairs for matrix Lie groups. And this notion of dual pairs also have application in hydrodynamics for dual pairs where the group are diffeomorphism groups or volume-preserving diffeomorphism groups. And also in the second reference by Balayer and Vosbacher, which connect these dual pairs. So a similar notion of all pairs with quantization. So in my setting, we are in infinite dimension, but basically we would like to mimic this example. And in this talk, I will just concentrate on one leg of this diagram here, and concentrate on the right action of a small group U1 of H plus. So U1 of H plus is a group of unitary operator on H plus, which differ from the identity by a trace class operator. And it acts on the right by the following formula. So either you take a right action and you don't put the -1, or you just want a left action and you put minus. The important point is that it's a precomposition by an element in the group. And there is this action preserved the symplectic form, and there is an Hamiltonian moment map associated to this action, which is basically the same formula as before. You see here I put a plus. That's probably the notation of Skerrit and Wiesmann are not the same as mine. Anyway, that depends how you relate the moment map with the symplectic form. If you put a plus or minus there, that makes a difference in the sign here. Yes, and moreover, so this moment map is invariant by the left action of a group that we have seen before, the group of unitary operators with block of the form identity plus trace class and of block Hilbert-Schmidt. So now what we want to do is do a symplectic quotient or Kähler quotient. And for this, I recall what a regular value of a moment map is. So this is an element of the, so recall that a moment map is defined on a symplectic manifold M with values in the dual of the Lie algebra of the group acting on M. So if we take an element in the dual space of this Lie algebra, Xi, we say that this is a regular value of the moment map if you take the inverse image of this element, then the differential of the moment map is surjective at each point x of this level set, and also the kernel of this differential admits a closed complement. When we have this condition, then we can perform the quotient space of the level set of the moment map by the group G, and this will give us a smooth space. So here, the element of the dual space of the Lie algebra has to be invariant by the coadjoint action, so that we can act so that the level set is stable by the action of G. So in my example, I'm interested in a special level set. So if I take the inverse image of a coefficient times a trace, and what we get is that this level set is a real Banach submanifold of MK, and it's stable by the right action of the group U1. And it can be identified with the following set. So this, the set of all x in MK, such that x star x is equal to K2 K squared times the identity. And another proposition is that the group U12 that we have seen before acts transitively on this level set. And so the conjecture is that these two groups, U12 and U1 of H plus, form a dual pair. So this is just a conjecture at this stage. There are many things that have to be checked. In particular, that the orbits of, yes, that the level set of one moment map is homogeneous by the other. So here we just prove this for a given pre-image, but for the notion of dual pairs, we have to prove it for any element in G star. So now I'll recall what a Kähler quotient is. This is a refinement of what a symplectic quotient is. The symplectic quotients were introduced by Marsen and Weinstein, and then this Kähler version was a refinement of this symplectic quotient by a lot of people, probably Donaldson and Kronheimer. I'm not sure about the history here, who was the first one to give this this refinement. In any case, it's well known in the theory of Kähler manifold, and it goes like this. We have we start with a Kähler manifold endowed with a Hamiltonian action of a Lie group G, so with a given moment map, which I call mu. So the group is supposed to preserve the Kähler structure, and also we take a regular at star invariant value of the moment map. This ensures that the level set corresponding to this value is stable by the action of G. And we also suppose that G acts properly and freely on this level set, so that to ensure that the quotient will be a smooth manifold. Then the quotient is not only a smooth manifold, it inherits a Kähler structure from the Kähler structure of M. So meaning that on the quotient there is a natural symplectic, Riemannian, and complex structure which are compatible. In the infinite dimensional case, we have the analogous theorem, but we have to add a condition on the tangent space of the orbit. Remember that in the case of a weak Riemannian metric, in general, a space and its orthogonal for this weak Riemannian metric are not in direct sum in the ambient space. So we have to ask for this condition in order to be able to get a Kähler structure on the quotient and also a smooth quotient. So in this case, the quotient will be a weak formally integrable Kähler structure on quotient. Sorry. Now, if we go back to our example, we had the space MK with a moment map for the group U1. the level set is this set of operators in MK, such that x star x is a multiple of the identity. And if we mod out by the right action of U1, then we get a Kähler manifold by this Kähler quotient procedure. Now we would like to identify this Kähler quotient with the connected component of H plus in the restricted Grassmannian. And for this, I will make a detour. I will first define what a stable manifold is. So if we start with a Kähler manifold with a group G acting on it, and we suppose that the group G, like in our case U1, has a complexified group. In our case, this will be GL1, so the space of invertible bounded operators which differ from the identity by a trace class. And we suppose that this complexified group acts also on the same space M, and that this action is holomorphic. So the action of the group G extends holomorphically into an action of the complexified group. And then we can define the stable manifold of a level set. These are the elements in the ambient manifold M, which are such that there exists an element in the complexified group which map Y onto the level set. So if you start with the level set and make GC act on the level set, you will get the stable manifold. In other words, if an element Y in the stable manifold can be mapped to the level set by an element of GC, the complexified group. So what is, yes, before giving you the example in our case, let me mention the theorem that links the Kähler quotient, so the quotient of the level set of the moment map by the action of the group G, with the complex manifold quotient of the stable manifold by the complex group. These two manifolds are identified are isomorphic as complex manifold. So the quotient space of the level set by the real group G is isomorphic as a complex manifold with this complex structure coming from the Kähler quotient to the complex manifold MS mod GC. So MS is a stable manifold and GC is a complexified group. In our case, the stable manifold, which correspond to the level sets that I have given before, is the set of operators in MK which are injective. And in my case, with a condition on MK, this is the same as the set of operator in MK, such that the determinant of Y star Y over K2 is strictly positive. So as complex manifold, NK mod U1 is the same as this stable manifold modulo GL1. And the last step is to identify the quotient with a restricted Grassmannian. And for this, I use the canonical basis I have defined at the beginning of this talk. And I will use this and simply map the stable manifold to the restricted Grassmannian using the range of the operator. So at an element Y in the stable manifold, we associate its range, its image. And this will map to the connected component of H plus in the restricted Grassmannian. And this is actually an holomorphic submersion, which is equivariant with respect to the action of U12, and also invariant by the action of GL1. So the surjection is simply obtained by considering the canonical basis of an element P in the restricted Grassmannian, which actually belongs to M sub 1, so with K equal to 1 in this case. So a corollary of this theorem is following: the Kähler quotient of Mk by the Hamiltonian right action of U1 can be identified with a Kähler manifold as a Kähler manifold with a restricted Grassmannian GR res 0. Now, this is what I wanted to say for the restricted Grassmannian. I will go a bit quicker for the cotangent space. So in this case, I need to recall what a hyper-Kähler manifold is. A hyper-Kähler manifold M is a manifold endowed with one Riemannian metric, G, and three real symplectic form, omega 1, omega 2, omega 3, such that the pair G omega 1 is scalar, the pair G omega 2 is scalar, and the pair G omega 3 is scalar. So to each of these symplectic form, there is a complex structure associated, E1, E2, E3. And these three complex structures actually form satisfy the identities of the quaternions. So there is an action of the quaternions on any hyper-Kähler manifold. So for this talk, you just keep in mind that there are three ways to express M as a Kähler manifold. The Riemannian metric is the same in each case, but the complex structure or the symplectic form varies. In this case, we can also define what moment map for a group action is. So suppose that you have a group G here in this finite dimensional version that acts on the manifold M and that preserves the three symplectic forms and with three different moment maps. So Hamiltonian with three different moment maps, which I denoted by mu1, mu2, mu3. And then you can take a regular value. So this big mu here, it actually has values in three copies of the dual space of the Lie algebra of the group. And if we take the inverse image of a regular value of this moment map, and if G acts properly and freely, then the quotient of the level set of this regular value by the group action is again a hyper-Kähler manifold. I give you the reference where this theorem can be found in finite dimension, and it was applied actually in infinite dimension also in this paper. In the Banach context for operator theorists, here is a version, a non-formal version, where we have to add a condition on the tangent space as a direct sum of different copies of the tangent space to the orbits with respect to each of the complex structure and with a complement. So this is just a technical assumption here. And in this case, we can do the same in infinite dimension in the Banach setting, and we get also that the quotient space of the level set of the moment map by the group G has a weak formally integrable hyper-Kähler structure. So let me go back to the example of MK. MK was a symplectic manifold, but also it's a tangent space, which actually we can embed into its cotangent space. And on the cotangent space, there is a canonical complex symplectic form, which we pull back on the tangent space, and we end up with this formula. So now we take pairs of elements Z1, Z2, which are tangent to the tangent space of MK, and we pair them like this. this gives a natural complex symplectic form. So the real part and the imaginary part of this big omega gives two real symplectic form. And there is a weak Riemannian metric which is compatible with these real symplectic forms, which is this one. And if you prefer to see what the complex structure associated are, these are listed here. So there is the second, so the first one is a natural complex structure of the cotangent space, but seen in the tangent space, so that's why there is a -1 here. And the second one, interchange horizontal and vertical spaces, and there is a third one, combination of these two. For all this real symplectic form, we can find a moment map, so I listed here the moment map. If you remember what the moment map was for MK, you can read it here in the first mu1. If you put big X to 0, you recover the moment map that we had before. And there are two other moment map for the two other symplectic forms. What is interesting is that the level set to a given, the level set corresponding to a given element here of the image of the moment map has this expression, and so we can perform the hyper-Kähler quotient, and this Q, the quotient that we get, actually will be isomorphic to the cotangent space of the restricted Grassmannian by the following map. So at a class of small x and big X, small x is in MK and big X is a tangent element at X. We associated the following element in the cotangent space of the restricted Grassmannian. First entry is the range of X. This was also the case before. And then we have a cotangent element here that we pair with the use of the trace with a tangent element. More precisely, this cotangent space can also be identified with a complexified orbit. And what I need here is this definition. The complexified orbit of the restricted Grassmannian, or the connected component of the restricted Grassmannian, is obtained by conjugation of the projection P plus onto H plus by any element of GL2. So this is a homogeneous space, GL2 mod out by the product of GL2 of H plus times GL2 of H minus, and it can be interpreted in the following way. It's a set of pairs PQ. P belongs to the connected component of H plus of the restricted Grassmannian, and Q belongs to the dual restricted Grassmannian when we exchange H plus and H minus, and the sum P plus Q is equal to H. Another way to express is that the pairs of P prime both are now in the restricted Grassmannian in the connected component of H plus, and P plus the orthogonal of P prime is equal to H. So now Q, the quotient, the hyper-Kähler quotient, can be also identified with this complexified orbit, and here I give you the formula for this. But I would like to understand this identification using Mostow decomposition theorem that I recall here. So this is a theorem of decomposition. Perhaps I don't need to go into details here because my time is over already 5 minutes ago. I'll just give the theorem that is written here. the group GL2 of H is homomorphic, or diffeomorphic actually, to the product U2 times XF, XE, and XF, F and E here are subspaces of the linear subspace of self-adjoint element in the Lie algebra of the group GL2, such that the bracket of X with the bracket of X and Y is inside E for any X and Y in E. So this is a condition on E, and F is the orthogonal of E in S2. So we have this kind of refinement of the polar decomposition, and we apply this. Oh, yes, I need to give some references. So there is a huge list of references. So these are historical references from the initial version of Mostow in 1955 to a version by Porta and Recht in 1984, another version in 05 by La Rotonda, Androschow and La Rotonda in 06, Conde La Rotonda in 010, Miglioni in 2014. I have also a version from a thesis also, and also published in 2023. And we have a version with Gabriel also in 24. So different version of the theorem, and either for infinite dimensional Lie group or for non-linear algebra or Finsler Lie groups. What I will need here is simply the decomposition here of the group, complexified group, where the E that was in the slide before is actually I times the stabilizer. For me, it was it's a stabilizer of the projection P plus, and M is its orthogonal. So we have the decomposition like this, and when the complexified group will act on the projection P plus, this first term will act exponential of AK trivially because K is a stabilizer, and we'll see that the orbit, complexified orbit, is fibered on the orbit on the restricted Grassmannian, where the fibers exactly this exponential of IMX. MX here is orthogonal of the stabilizer of point X. I'm sorry, I cannot go far with this identification. I wanted to speak about scalar potential, but my time is over. I just wanted to give you some formulas where you see that I need determinants of elements like X star X. X is in the affine space MK I had before. This is why, in order to be able to write this potential, I need the space MK, where the first block is identity plus trace class. So this makes this formula valid. This allows me to write this kind of formulas. And for other complex structure, we have other kind of potential that a potential is a function that encodes the corresponding symplectic form. I think I will stop here.